Hello everyone. In this video we are going to learn about Simplified Instructional Computer. What is Simplified Instructional Computer? It is a hypothetical computer, means it is an imaginary machine which has been carefully designed to include the hardware features that can be found on most real machines, while avoiding all irrelevant complexities that are found in machines, which are different from architecture to architecture. Like many other products, SIC also comes in two versions, the standard model and the SIC XE model. XE stands for extra equipment. I repeat, XE stands for extra equipment. It has got more features than SIC, with all features of SIC included in it at some extra cost as well. So I can say XE stands for extra expensive also. And the two versions has been designed to be upward compatible. What do you mean by upward compatible? The object program written for SIC runs well in SIC XE machine as well, perfectly fine with no modification at all. Now, the programmer's model of any architecture, if you have to study, requires a careful detailing on the following features. The features are memory, registers, data formats, instruction formats, and addressing modes, instruction set, input and output. When I say memory, we need to understand what is the total address space available for storing code and data. When I say register, we need to know how many number of registers are present, what are their sizes, etc. When it comes to data format, what type of data your architecture can handle. When it comes to instruction format, what is the size of instruction, every instruction supported by the architecture, what is its format. When it comes to addressing mode, what is addressing mode? Addressing mode is the method to specify operand of an instruction, because the operand can be present either in a register, it can be present in a memory location, or it can be present in the instruction itself as part of the instruction itself. The addressing mode specifies how to calculate the effective memory address of an operand. Next feature is instruction set. What instructions are available? What instructions are available in the architecture? Are we having support of arithmetic operations? Are we having support of logical operations? Are we having support of input-output operations? And so on. What are the different instructions available in an architecture? And finally, how the architecture can communicate with the outside world. Architecture, communication to outside world. How it is supported? Outside world. How it is supported? With the help of input-output operations. So these are the 7 dimensions we need to understand when we have to study any architecture, if we have to write program based on the architecture. Now coming back to our SIC machine, we will be studying these 7 dimensions. The first one being the memory. So what is memory? Memory is a storage which is, you can visualize the memory here. They are divided into byte. We call it as byte addressable. Consecutive 8 bits we call as byte, and consecutive 3 bytes we call it as word. Right? And how much of memory is available in our SIC machine? You can see in this slide we have total of 2 power 15 bytes of memory available in the SIC machine. 2 power of 15 byte is equal to 32,768. So if you have to address any word present in the SIC machine, you just need to know the lowest number byte. Using that address, you can access the 3 consecutive bytes from there. This is about memory. The second dimension that we need to understand is registers. In SIC, there are 5 registers available. The 5 registers are having different names as well as numbers. We need to remember both the names and numbers. This is very much required for our further course. Okay, so what are the names? The names are, we have accumulator, A stands for accumulator. Next type of register is index register. Mnemonic used is X. Next we have linkage register named as L. We have program counter. We have status word. Why this A register is required? For performing arithmetic operations. Index register is used for addressing. This is specially helpful for performing array operations. Then we have linkage register. We have an instruction called as JSub instruction, which will help you perform jump from one subroutine to another subroutine. This is subroutine 1, this is subroutine 2, for example. You can perform a jump from one subroutine to another subroutine. And if you want to return back to the same subroutine, you will have a return statement here. That means you need to remember the address before performing this jump. This address, these instructions address will be stored in linkage register. So the return instruction can use this contents of linkage register and perform jump to the subroutine back. Next type of register used is program counter. We all know it contains address of the next instruction to be executed. Next is status word. This is similar to the flag register which you might have studied in your earlier course. It contains variety of information including condition code. Please note SIC does not have any stack, so it will make use of linkage register while performing the subroutine jumps. So the next dimension is the data formats. The data types supported in SIC are characters, which are 8 bits in size. They are represented using ASCII codes, and we have support of integers. Both positive integers and negative integers are supported. When it comes to the negative number, it is represented using 2's complement notation. And also please note there is no support for floating point numbers, but this drawback has been filled in SIC XE. So next is instruction format. Next is instruction format. All instructions in SIC are 24 bits in size. All the instructions are of same size. They are 24 bits. And how this 24-bit format looks like? It will have 8 bits of opcode, and there is 1 bit which will specify the addressing mode, and we have 15 bits. We have 15 bits for specifying the address of operand in memory. Address of operand which is present in memory. What do we mean by this? How to understand whether this 15 bits is sufficient to address all the memory available in SIC? How to understand? Let me just give an example for that. Okay. Let's consider that I have 2 bits to specify the address. Instead of this 15 bits, I have 2 bits. So what possible addresses I can frame out of this 2 bits? I can have 0, 0 as one address, I can have 0, 1 as one address, 1, 0 as another address, and 1, 1 as another address. So with the 2 bits, how many addresses I can frame? I can frame 4 addresses which can point to 4 different locations. 4 is nothing but 2 raised to 2. Okay, I can have 2 raised to 2 number of addresses. Similarly, if I have 3 bits, so what are the possible addresses that I can frame out of 3 bits? 3-bit addresses will have the format ranging between 000 to 111. That means I can have 8 number of addresses out of 3 bits. 8 is nothing but 2 raised to 3 locations. I can address 2 raised to 3 locations using only 3 bits. Now I have got how many bits for specifying the address? It is 15 bits. If it is 15 bits, how many addresses we can frame? It is 2 raised to 15 addresses we can frame. If you remember, what is the total memory available? In SIC, it is 2 power 15 bytes. Now for every byte, we can have the address with the help of this 15 bits, right? So now coming back to this X bit we are having, if it is only 1 bit, 1 bit means we can have only 2 possible values. Either this X bit will be 0 or this X bit we can have a value of 1. If X bit is 0, we call it as direct addressing. If X bit is 1, we call it as indexed addressing. Indexed addressing. Here we have the table. If it is a direct addressing mode, the operand is present in memory and its address is directly specified in the instruction itself. This 15-bit address is the address of the operand in memory. And in case of indexed addressing, which is useful in accessing array elements, the operand can be found in memory at the address calculated as sum of this 15-bit address specified in the instruction with contents of the index register. So let me just summarize. The instruction formats, all instructions are of equal length, 24 bits. And the instruction format is we have 8 bits of opcode followed by 1 bit which will specify the addressing mode, followed by 15 bits for specifying the address. This 1 bit which decides addressing modes. 1 bit means only 2 possibilities, either it can have 0 or 1. 0 means direct addressing, 1 means indexed addressing. Direct addressing means you don't have to calculate anything, directly you have the address of the operand, use that operand, perform the required operation. If it is indexed addressing, then what we have to do, take that 15-bit address, add it with the contents of the index register. Now you got the actual address of the operand, take the operand from that address, perform the required operation. And next feature that we have to understand is instruction set. The first category of instruction available is load and store instruction. What do you mean by load operation? If you are loading register from the memory, you are loading some contents from memory to register, we call it as load operation. What do you mean by store operation? You are loading or you are storing the contents from register to the memory, we call it as store operation. And now you can see few examples available in SIC for performing load and store. LDA stands for load accumulator. Load accumulator with the memory contents as specified in the instruction. For example, LDA alpha, it says that alpha is a memory location, load 3 consecutive bytes from alpha to the register A. Next I have LDX. LDX means what? We are loading the index register from the specified memory location. Similarly, we can have LDL. LDL stands for load linkage register. Similarly, what is STA? Here we have an example of STA alpha. What do you mean by STA alpha? Accumulator contents, which is 24 bits, has to be copied to memory location named as alpha. 3 consecutive bytes. Right? STX means store from the index register. Similarly, I can also have an instruction called as STL. These are various load and store instructions available in SIC. Next category of instructions available are arithmetic instructions. And all arithmetic instructions, they will involve register A by default and as one operand, and another operand will be present in memory. So what are different arithmetic instructions available? We have add, we have subtract, we have multiplication instruction named as MUL, we have division instruction available as DIV. Here is an example. We have to write an instruction like this: add alpha. What do you mean by add alpha? That is nothing but 1 is an inherent operand, which is accumulator. Accumulator contents has to be added with the alpha and result will be stored in accumulator itself. And next category of instruction is comparison instruction. Again, the comparison instruction involves accumulator as well as word in memory, and whenever we perform the comparison operation, the comparison result will be stored in condition code. Where is this condition code present? It is present in a register called as a status word. Okay. So now here is an example. COMP is an instruction for performing comparison. Compare alpha. What are we trying to compare here? Only one operand can we compare? No, another operand is default operand, which is accumulator. Accumulator contents are compared with the contents of alpha. Accumulator may have bigger value when compared to alpha, then condition code will be set like this. Accumulator contents can be less than alpha, condition code will be set equal to less than. Both the contents are equal, then CC will be set to equals. So this is how comparison instruction works. It will have an impact on condition code, which is present in status word register. Next category of instruction available is conditional jump instructions. Based on the condition code, we will perform the jump. It will test CC and it will perform the jump accordingly. If CC is set to less than, then this instruction can be used. Jump if less than. Similarly, we have jump if equals. Similarly, we have jump if greater than. These are the conditional jump instructions available. And next and the last category of instructions available in SIC is a subroutine linkage instruction. Already I have discussed about the subroutine linkage. We have subroutines like this. This is subroutine 1. This is subroutine 2. What happens is you are executing this program. Here you will perform J sub SUB2. What happens when you execute J sub SUB2? This subroutine execution has to be temporarily suspended. Control has to be given to subroutine 2. And as the last statement in subroutine 2, we will have return statement. Return statement. In SIC, the return statement will be R sub. Return back to subroutine. Where it needs to return now? Where it needs to return, it will remember the return address in the linkage register before it performs the J sub, right? So J sub jumps and places the return address in register L. What does R sub do? It returns to the address in L. So these are the various types of instructions available in our SIC machine. last dimension that we need to understand about the SIC architecture is input and output operations. Input and output operations are performed by transferring 1 byte at a time to and from the rightmost 8 bits of register A. So there is a device, IO device. We have an IO device, we have accumulator which belongs to SIC machine, right? So you can perform the data read and write. Both direction data transfer is possible with the SIC machine, but at a time we can transfer only 8 bits, that is 1 byte. So each device has assigned a unique 8-bit code. Each device will have a unique address. Each device will have a unique address, and that address will be how many bits? 8 bits. 8-bit address, right? And there are 3 instructions available for performing input-output operations. The first instruction is test device. It will test whether this input device or output device is ready to send or receive a byte of data. There are only 2 cases. Device should be ready or device is busy with some other operation. If device is ready, condition code will be set equal to this symbol. And if device is busy, condition code will be set as equals. If device is ready, then you can perform read operation or write operation based on input or output device you are handling. And if device is busy, you cannot proceed read or write operation. Instead, you have to wait until device becomes ready. So these are the 7 dimension that we have understood about the SIC architecture. So in the next video, we are going to learn SIC XE machine architecture by keeping these 7 parameters in head. And please note, SIC XE is upward compatible. SIC is upward compatible with SIC XE. That means the features available in SIC is also available in SIC XE, but it comes with little extra equipment. All the features that we have studied will be there in SIC XE machine also, but it will also have some additional features that requires a detailed study that we are going to do in our next video.